Budgeted from 5 to 8 minutes for each of you, and we hope that you will hold to that. I'll try to take a look at the clock and give you a hand signal if not. And if also, because we're recording this, could you use a speaker, either the one that you pin to your lapel or this speaker, because or use the handheld or this. Okay. All right. So our first lightning speaker will be Jeremy Vasella. Jeremy is a senior computer science student and is also pursuing a minor in cybersecurity. He's going to give a demonstration for us.
How do you adjust this? Sorry. So I'm Jeremy, as you all just learned, and I work in the IT department in the Chafee building, which is across the other side of the campus. And I'm going to give just a very brief talk about how, even in the undergraduate level that I'm at, supercomputing, our projects start to wander into the realm of supercomputing or high performance computing. Just start to enter the outskirts of it. And what we do at the Chafee lab right now, one of our projects is modeling the ocean floor, and then eventually with the aspiration to model the water columns that will be on top of the ocean floor. And these models are constructed for both visual aids, for teaching aids, and also for simulation. And of course, those require two different, levels of computation. So we get our model data in two different forms. One form is a basically giant texture of height map data. It comes to us in either image files or just text files. And the other type of data we get is LiDAR pole data. So the texture height map data is considered low resolution. It's 1 kilometer per pixel sort of resolution. And the LiDAR data is much, much higher, pulled by laser satellite sort of stuff. And we have to manipulate these data these sets of data to construct models with which we can use for both visual and simulation stuff. We're not quite at the simulation stuff yet. We're still working on the visual level. So when we try to construct these models, we have to perform a variety of operations on data, of course, clamping values, interpolating between values, and we found we have to work at really low resolutions, even just on the low resolution height map data, and we can't even approach the LiDAR data correctly. So when we interpolate the values or scale them, we're using that to set up, even on just the visual model scale and not the simulation scale. We find the operations we're performing are kind of slow, and not even talking about rendering these visual models, but more so setting up the data so that we can render these visual models. So I have just really, really short two little videos that just show the resolution we're working at now that's taking time to render, not so much render, but construct the model data for. Oh, that's right, you put it in VLC over there. Any ideas what's going on with that? All right. In any case, all right. Again, these are really short. This is the resolution. You can barely see it, but in essence, this is the resolution we're working at. It's kind of high-level, low-resolution stuff, and even in this, creating the data that sets up those models. I'll just pause it right here so you can see what we're talking about. This is modeled after the height map data up here. So we just basically took the data we got for the textures and projected it on the sphere. And the operation to create that took quite a while. And it wasn't using LiDAR data, just with the texture data. And if I have a second picture of the Straits of Gibraltar, but it's essentially the same thing. when we attempt to construct the models for these things, it takes a long time. And then additionally, when we try to render them, even with our distributed rendering solution, it takes a significant amount of time. If we approach the LiDAR data, which is higher resolution, which is more what we want to accomplish and to use, and something we will need to use if we want to simulate it, we're hitting CPU bottlenecks that are problematic. So in essence, even in this undergraduate just trying to make teaching models and some very light simulation models, we've hit bottlenecks in CPU power. And this basically just demonstrates that as the projects we're doing, as we try to make more sophisticated models and try to do more sophisticated things, the need for higher computing power is just going to amplify. So, any questions?
I have a quick question. What do you think? What do you think you need in order to do this? I mean, do you have a clear picture of what you mean by more computing power?
Okay. Sorry, did you finish the question? Didn't mean to cut you off there.
Yeah, no, it's basically there's a gap between what you want to do with this data and your knowledge about how to do that. So is that gap wide for you or narrow?
Just from very quick background about this, I have a coworker who's the one who's making most of these models, and I helped him at the beginning with the data set, so the LiDAR data or the other stuff, and basically transforming that data. And he has been the one reporting to me where we're hitting bottlenecks and where we're hitting these things. And essentially, we're having issues when we attempt to apply transformations or projections to the LiDAR data in particular, because the data set it's multiple, like it's absolutely massive, orders of magnitude larger than the texture stuff. And I completely forgot your question. So,
do you think you know enough in order to get past your current technical difficulties, or do you need assistance with technical issues?
So you're saying more so, are there other approaches we could take to break down this so that we wouldn't? I'm sure enterprising, many clever people could come up with a way to break this down more. But the tools we have and the capacity we have currently, they can't brute force through it fast enough. So if we had, for instance, the distributing render solution we have to render our models out, it's got about 100 cores over the course of all the computers. And if we had more cores at our disposal or more computing power at our disposal, we could use the tools that we already have in place and set up to render these models out, instead of having to develop our own tools for that specific purpose when we're trying to instead direct our efforts towards establishing the models. Thank you.
Next we've got Peter Cornelian, Professor of Oceanography from the Bay Campus. Can I roll with it? I'm a roll with it. Good forward. Got it. Okay, I'm a satellite oceanographer, and I'm interested in using satellite data for the oceans. One of the question I asked earlier about storage is because my needs, my primary constraints are really storage. What I'm going to do is I'll go through two different categories of processing that we do and what our demands are right now. And they fall into two categories. I said satellite retrievals. We have a suite of programs that convert satellite derived brightness temperatures, I'll show you what that is in a second, to sea surface temperatures. And the other is where we look for fronts and gradients in the ocean, and I'll try to give you a sense for that. And we have a suite of programs that do that as well. Basically, we start off with measurements in several different spectral bands from the satellite. Satellite goes over it, makes these measurements. and we convert them to sea surface temperature. And this shows sea surface temperature averaged over a year from one of the satellite's receiving stations. So that's the processing that we do. And we do that, we're doing that on a number of different archives. We're looking at the Western North Atlantic. We have data from 1981 to 2014. That's this red blob here. Each image is about 8 megapixels, and there are about 170,000 images in this particular archive with a data volume of on the order of 7 terabytes. And the time to process this through all of our algorithms is about 570 core days. That's on my on one of our Macs, any one of our Macs. And then we have a number of different archives. We have hello. Oh, maybe now what do I do? Should I put it closer, further? So we have data from the eastern North Atlantic, which I don't show here. It's another 115,000 images. And I have data from the western North Pacific, the eastern North Pacific, and the south and the eastern South Pacific.